Hello everyone, welcome to my channel Coding Together. My name is Vikas Oja. Today we will see another Leetcode problem, that is lowest common ancestor of a binary search tree, LCA. So it's a medium level question and it's a very popular question, as you can see from the likes. So let's read the problem statement. We are given a binary search tree, BST. We have to find the lowest common ancestor, LCA, node of two given nodes in the BST, right? So we are given with the two nodes and we have to find the lowest common ancestor. So what is the lowest common ancestor? The lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T that has both P and Q as descendants. So whichever is the lowest node having P and Q as descendants, that is the LCA. And we allow a node to be a descendant of itself. So a node can be a descendant of itself also. So if you see this example, like this is a BST, binary search tree, right? And we are given with P equal to 2 and Q equal to 8. And we have to find the LCA, lowest common ancestor. So 2 and 8 are the descendants of 6. So 6 is the lowest common ancestor, right? For this, again, if you see, we have given with P equal to 2 and Q equal to 4. So now if you can see here, the 2 is the root of 4, right? 4 is the descendant of 2. So now this statement where we allow a node to be descendant of itself. So here so 2 is also a descendant of itself and 4 is a descendant of 2. So that's why 2 is the lowest common ancestor for 2 and 4, right? So some constraints that we have to remember, that P and Q will exist in the BST. So always P and Q will exist in the BST, right? And all the node values are unique, right? Now let's see how we can solve this problem. So we will use recursion, right? We will use recursion. So for the recursion, we will use recursion on trees, and we are given with BST, binary search tree. So there is an important property of BST, that is left value should be smaller than the root value, and the root value should be smaller than the right value, right? Left child or left descendant must be smaller than the root, and root must be smaller than the right child or the right descendant. Now there can be 4 conditions approximately, like the P and Q, the descendants that for which the LCA we need to find it. P and Q can lie on the left subtree, right? They can be smaller than a root node, right? So we have to move left, then we'll move left for our recursion. And now if P and Q can lie on right subtree, right? So we'll move right. Also, third possibility is P can lie on left and Q can lie on right, or vice versa, right? So what we will do, we'll return our root element. So because this is our favorable condition, because whenever the root will give you the LCA. Root is the LCA, because root is the LCA for this P and Q whenever this third condition meets. Or also if the fourth condition, whenever one of the P or Q is equal to root, then also we'll return root, because then in this case also root will be LCA. root will be LCA. So let's see these conditions with an example, right? So if we have, like, suppose p is equal to 3 and q is equal to 5 here, and we will start with the root nodes and we'll compare that. If you see p and q are smaller than 6, so we'll move left, meeting the first criteria, right? Because 3 and q are lying on the left subtree, so we'll move left. Now at 2 again we'll check, so they are, p and q are greater than 2, so it's meeting the second criteria, we'll move on right. Now at 4 we will check, so 4 is greater than 3 and smaller than 5, right? So it is the third condition that is moving. So what we will do at the third condition, will return the root, right? So if we see here 3 and 5, so 3 and 5 are the descendants of 4. So 4 is the lowest common ancestor for 3 and 5, right? Because 3 and 5 are the descendants of 4, so it is meeting this third criteria and will return root, right? 3 lies on the left subtree and 5 lies on the right subtree. So we'll return root 4 from here, and then it will return 4 and return 4, right? So now suppose we take the same example. If we take the same example and we change we change p is equal to 2 and q is equal to 4, so here you will see it will meet the fourth criteria. It will meet the fourth criteria. How? We'll start with 6 again. So 2 and 4 are smaller than 6, so we'll move on the left, right? The first criteria, right? Now again at 2, now here's, you can see that 2 root 2 is equal to one of the p or q, so p is equal to root node. So fourth point, whenever one of the p or q is equal to root, will return root, right? Will return root, because 2 will be the ancestor for 4, and 2 is an ancestor for itself, so we'll return 2, and finally from 6 it will return 2 when we backtrack, right? So this is the recursion. This is how we solve this problem with using recursion, using considering the properties of BST and some conditions. So let's see the code part of it. It's very simple. What we designed, whatever our conditions was, so if p dot val is less than the root dot val, or q dot val is less than root dot val, means it's in the left subtree, right? If it is in the left subtree, we'll go again recursively call the method with the root dot left, right? We'll move to the root left part. Else if the p dot val is greater than root dot val and q dot val is greater than root dot val, then we'll move on the right part. So we'll call again the same function recursively with root dot right value. Else in either of the case, like it will be 3 or 4, we'll return the root element. Let's run this solution. So yeah, test cases are accepted. It means the solution is working fine. So let's see the time complexity for this algorithm. So the time complexity is dependent on the nature of the tree, the BST that is given. So BST, if the BST is given as balanced BST, right? So for a balanced BST, the P and Q, the descendants for which we have to find the LCA, would lie on the left subtree, on the right subtree, and whenever they lie on the left and right both, or vice versa, we return the root, as we saw in the third and fourth point. So we are not traversing each and every node in this tree. So the time complexity will be big O of h, where h is the height of the tree. H is the height of the tree. Now what is the average height of a tree? Average height of a tree we know is big O of log n, right? Big O of log n, that is the average height of the tree. So the time complexity will be big O of log n for average case, that is for balanced BST. And for the worst case when the BST is unbalanced, right, or what we call as skewed. So means that all the nodes are on the left side or all the nodes are on the right side. The worst case time complexity will be order of n, as the height of the tree is big O of n for this. So the worst case time complexity will be big O of n. So for the space time complexity, it will be the same. For the average, it will be order of log n, right? And for the worst case, big O of n. So I hope you like this video. If you like this video, please share and subscribe. It will be keep me motivated to bring more such videos in front of you. Thank you guys. Bye.